successes and remaining n minus x failures. So exactly x successes you obtain. So in this particular case, probability of this x successes and consequently remaining n minus x failures. So since they are independent, all trials are independent, probability of their joint occurrence is equal to product of their probabilities. So probability of S is P. Again this P how many times? X times. And probability of these failures are Q, that will be n minus x times. So it will be P raised to x, Q raised to n minus x. So this is the probability of exactly x successes in this particular order. Suppose order is changed. Here it is F, here it is S. So again we have exactly x successes. Again here it will be Q, here it is P, but ultimate value will be same. So there are NCX different ways, and for each of these ways probability of exactly x successes remains same as P raised to x into Q raised to n minus x. Now either x successes can occur in this way or previous way. These are or means addition. So every time probability is same, and or means addition, so it will be added how many times? NCX times. So ultimately that becomes NCX P raised to x Q raised to n minus x. This is the probability of exactly x successes in any order. This was the probability of x successes in this specific order. This is the probability of x successes in n out of n trials in any order. So this is now considered as probability mass function of binomial distribution. So a random variable x is said to follow binomial distribution if it assumes non-negative integral values and its probability mass function is given by Px is equal to NCX P raised to x Q raised to n minus x, where x can take value 0 up to n. Remember that this probability I write 0 to 1 may be equal also, and this Q is equal to 1 minus P and 0 otherwise. So remember that when you are asked to write probability function, then you always write all these things. Since x take different values 0, 1, 2, it cannot take any value between 1 and 2. So this is discrete distribution. Now here n, that is number of independent Bernoulli trials, P, that is probability of success at each trial, Q, that is 1 minus P, that is probability of failure for each trial, and X, that is number of successes. So this way, here in this case n and p are called parameters. Independent constant n and p are called parameters of this distribution. Once we know the value of n and p, we can find probability of any number of successes. Now in sums, to solve the sums of binomial distribution, of course that will be taken by Professor Patel, but I just want to say that by reading any sum, you have to just determine the value of n, p, x, and especially values of n and p, values of their parameters. So remember that when you read the sum, then first of all you determine the value of n. What is the value of n in that particular sum? That is number of independent Bernoulli trials, how many trials are taken. Then p, probability of success. So the event whose probability is to be obtained should be taken as success, and we have to find probability of that success for one particular trial. Q, that can be automatically obtained by 1 minus p, and x, how many successes are required, number of successes. So in this example, any example of binomial distribution, you just find out the values of n, p, q, and x, and just substitute the values, you will automatically get the exact answer. Now when we take x is equal to 0, nc0 1, p raised to 0 1, q raised to n. For n x is equal to 1, it is nc1, p, q raised to n minus 1. for 2 NC2 P square q raised to n minus 2, and last NCN1 q raised to n. So actually these are the values for different values of x running from 0 to n. So these are different terms of the binomial expansion of q plus p raised to n. So probabilities for different values of x are nothing but different terms of the binomial expansion of q plus p raised to n, and that is the reason why this is called binomial distribution. Remember that this sigma px, if you find, it is always 1, because ultimately sigma px becomes sigma x running from 0 to n, this ncx p raised to x q raised to n minus x, and ultimately it becomes q plus p raised to n, because it is expansion of this, and q plus p is 1, 1 raised to n is 1. So this way total probability is always 1. Now x values and their probabilities, say 0, 1 up to n, and particularly some value, say x general value. This is q raised to n, nc1 q raised to n minus 1 into p, and p raised to n. So x values and corresponding probabilities are given. So you can write in this fashion also. The distribution can be written in this form also, or in formula form, which we have written earlier. That is another form to write this distribution. Now to find mean, actually mean is expected x. So that is the formula sigma x px, that we know. If you find mean, it will be np. Similarly, we can find expected x square, then variance of x, that is expected x square minus cx square. If you find this value, it will be npq. Remember that q is less than 1, so multiplying this quantity by the quantity which is less than 1 will become smaller. So npq will be smaller than np, so mean will be always greater than variance. So remember that for binomial distribution, mean is always greater than variance. So this way we can find other moments also. Then other concept is moment generating function. That is nothing but expected value of e raised to tx. So if you find this sigma x running from 0 to infinity, 0 to n, e raised to tx, px means ncx, p raised to x, q raised to n minus x. If you find this value, this is q plus p raised to t raised to n. So if you differentiate this one time and put t is equal to 0, you will again get first moment np. Differentiating second time and putting t is equal to 0, we can get mu2 dash. So from this also we can find moments of various orders. Then we can find from the row moments, we can find central moments. Say variance mu2 is npq, mu3 is npq into q minus p, that you can easily find. Mu4 is equal to npq into 1 plus 3 into n minus 2 into pq, and so on. So generally we find first 4 moments only for any distribution. From this we can find beta 1 mu3 square upon mu2 cube, then beta 2 mu4 upon mu2 square. If you find this value, and here if you take n tends to infinity, then you can easily check that beta 1 is tends to 0, beta 2 tends to 3, which is the case of normal distribution, which we are going to take afterwards. So actually binomial distribution generally tends to normal distribution for large value of n, remember. If you find mode of this, actually if n plus 1 into p, we don't derive actually, but I just give the result. If this is not an integer, then box of this, say m. So m will be the mode of this distribution. In this case, the distribution is unimodal. There is only one modal value, unique modal value, and that is m, which is box of integral part of n plus 1 into p. If it is integer, suppose n plus 1 into p is integer, then the distribution is bimodal, there will be two modal values, and suppose if it is integer, then box of this is same, so I call it m only. So in that case, m and m minus 1, this will be the two modal values. So depending upon whether this n plus 1 into p is integer or not, we can have unimodal or bimodal distribution. So this is about, there are certain other properties also. Now under certain conditions, this binomial distribution approaches to Poisson distribution. So the Simon de Poisson has obtained on his name Poisson distribution. Generally correct name is Poisson distribution, but we call it Poisson distribution under three conditions. Say first condition is that n should be very, very large, means n should tend to infinity. Second, p should be very, very small, so p should be almost 0, near to 0. And third, see, infinity into 0 undefined. Anything into 0, that is 0. Anything into infinity is infinity, but here infinity into 0 is undefined. But then also we assume that np is equal to lambda, say, that is a fixed quantity. Remember, this is fixed, definite number, definite quantity. So under these three conditions, when n tends to infinity, p tends to 0, and np is equal to lambda, then Simon de Poisson proved that binomial distribution whose probability function is this ncx p raised to x q raised to n minus x. This approach is to Poisson distribution. Now here I can easily derive also, but just we omit the proof of that. This will become e raised to minus lambda when we take limit as n tends to infinity of px. So this becomes e raised to minus lambda, lambda raised to x upon x factorial. Remember that in binomial it was 0 to n, but n tends to infinity, so it is 0 up to infinity. So here this is the now probability function of Poisson distribution. So a discrete random variable x is said to follow Poisson distribution if it assumes non-negative integral values and its probability mass function is given by, say, px is equal to e raised to minus lambda, lambda raised to x upon x factorial, x running from 0 onwards, 0 otherwise, and where lambda is positive. If probability function is given by this formula, then we say that x follows Poisson distribution and notation is p, and generally we write parameter lambda in the bracket. So x follows Poisson with parameter lambda. Here also one interesting property is that expected x is lambda, means mean is lambda, mu and s. We know how to find mean, variance, etc. That I explained also in binomial. Same procedure is to be applied. Variance mu to variance of x is also lambda, variance. So remember that mean and variance both are equal for this particular distribution. There is one another distribution also which we are going to take afterwards, not in this lecture. But here especially mean and variance are equal. In binomial distribution mean was greater than variance, here mean and variance are exactly equal. Even third moment is also same as lambda. And here also if you find beta 1, beta 2, then beta 1 tends to 0 for lambda tends to infinity, beta 2 tends to 3 as lambda tends to infinity. So again it will approach normal distribution. If you find mode, suppose, I don't give the procedure just now, but if lambda, which is the parameter actually, if lambda is not an integer, then take m is equal to box lambda. And in this case, when lambda is not an integer, then the distribution will have only one modal value, and that is equal to m. If lambda is an exact integer, then also you call lambda is equal to say m, and in that case there will be two mode values. So distribution will be bimodal. Again m means lambda, and lambda minus 1 means m minus 1 will be the two different mode values. These are the two modal values. Remember that if x1, x2, see here, if x is Poisson with parameter lambda, then here moment generating function is expected value of e raised to tx. So that value is e raised to lambda into e raised to t minus 1. Again, from this also we can find moments of various orders. If x1, x2, xn are independent, say these are n independent variates such that each xi is Poisson with parameter lambda I, then sum of this distribution of this summation sigma xi is also Poisson with parameter sigma lambda I. In binomial distribution, similar property is there. If all xi are binomial, if x follows binomial with parameter n and p, generally we write x follows binomial with parameter n and p. So here, if xi is binomial parameter ni and p same, then also sigma xi is also binomial with parameter sigma ni and p. Here, if x1 is Poisson with parameter lambda 1, suppose x2 is Poisson with parameter lambda 2, if x1 and x2 are independent, then x1 plus x2 is Poisson with parameter lambda 1 plus lambda 2. But if we take the difference x1 minus x2, that is not Poisson. So sum is Poisson, sum of two independent Poisson variate is Poisson, but the difference is not Poisson variate, remember. So there are several other properties also of this binomial and Poisson distribution, but just now we go for their applications and actually examples where these two distributions can be applied. So I request Professor M. N. Patel to explain these properties, actually applications of these two distributions.